For those of you just joining in now, my name is David Lewis and I work at Easy Power. And today I am presenting the AC interference in shared corridors presentation. And I want to invite people as we're going through this presentation to use the questions interface as a part of the meeting to enter questions, and we'll address them as they come. And we'll be able to address questions at the end of this presentation as well. So as we're going into this presentation, I want to highlight that we're covering a lot of areas in relatively light detail, and there's a lot of information or more details that could be their own full presentation. But I want to, in this presentation, kind of discuss the general effects that a transmission line can have on adjacent facilities and provide some guidance or some tools for evaluating AC interference. And it's my hope that at the end of this presentation, you'll be able to describe the physics of AC interference on adjacent facilities, that you'd be able to explain the types of hazards that can occur from AC interference, and be able to understand and develop a process for evaluating and mitigating these types of hazards. In order to accomplish that, we're going to talk about the physics of AC interference. We'll discuss some of the recipients of AC interference and go into some of the data requirements of a couple of them. We'll also highlight or do a brief overview of the evaluation or analysis process and do a quick sample of a case study. So first, let's talk about the physics of AC interference. And when we're looking at this, there are three types of modes or coupling methods that we see from AC interference. We have the inductive coupling, which is based on the magnetic field. We have the capacitive coupling, which is based on the electric field. And we have the conductive coupling, which requires some sort of physical contact or medium for current to flow from the transmission line to the recipient object. So talking a little more detail about the magnetic field, when we have an alternating current, this is producing a changing magnetic field. And what can occur is that changing magnetic field can induce a voltage on adjacent parallel objects. As illustrated at the bottom, if we have an AC current flowing through a wire, it's going to develop a magnetic field, and that will induce an opposing current and voltage on a parallel wire. Some things to note about that is that induction is going to be an effect for parallel objects. You won't see this induction occurring on things that are intersecting at 90 degrees. And some general relationships to be aware of is that as you increase the current, you're going to see a linear increase in the voltage that you're inducing upon that parallel object. Similarly, if you increase the exposure length, you're going to see a linear increase in the induced voltage. And if you're changing the distance from your transmission line to the recipient object, that's going to result in a nonlinear relationship. And you can kind of see that from the equations on the right. We have the magnetic field strength, which is the permeability of free space times the current over the distance from the wire, and how much that changes in a relative period of time is going to determine your induced voltage on that adjacent object. So you can have much greater field strength changes in a little bit shorter distances from that transmission line. Now, our other coupling effect is a capacitive coupling, and this is going to be driven by the electric field. And that's determined from that voltage level, and that's going to drive that field strength. This is not necessarily going to be a parallel object that is going to be the recipient of capacitive coupling. It's really going to be dependent upon the surface area that is exposed to the voltage. But one thing to note is that electric fields don't pass through grounded objects. So if you're having a pipeline or even a rail that's just above the Earth's surface, that electric field is really not going to drive much voltage on that type of recipient. And our third type of conductive coupling, going in a little more detail, we have our conductive coupling. Here on the right, you can see a export from XGIS lab. We have a transmission line that's experiencing a fault, and there's a ground potential rise from that fault current, and that ground potential rise is conductively coupling or transferring its voltage and current to an adjacent pipeline, elevating that pipeline's voltage and transferring that out. And because we're talking about AC interference as it relates from a transmission line to other objects nearby, in our power system we use three-phased balance systems. And that means that we're going to have balanced current on each of our phases, which results in a balanced magnetic field. But the difference is that the magnetic field strength is going to be dependent on its relationship or its distance from each phase conductor. So if you are able to make each phase conductor tighter, you're going to see a greater cancellation between the magnetic field. But if you're having each of those phase conductors spaced farther apart, like you would for higher voltages, you're going to see greater magnetic fields resulting from or along that transmission line. To illustrate that, we have that same delta phase configuration for two transmission lines. One of them has a 20-foot separation between the phase conductor on the top of the pole and on the bottom of the pole, while the other has a 30-foot separation between the phase conductor at the top of the pole to the bottom of the pole. And when we look at the magnetic field strength just above the Earth's surface, we can see that the tighter phase configuration, represented by this orange line, is going to have 40 to 50% lower peak magnetic field compared to the larger phase spacing. And it should not be a surprise to say that when you change the geometry of those phase conductors, you're dramatically affecting what that magnetic field looks like along the right-of-way. So again, we have our orange line representing our delta transmission line configuration. Our horizontal or H-frame configuration is represented by this gray line, and we can see much greater magnetic fields along the right-of-way. And this is because we're not seeing as much phase cancellation or magnetic field cancellation between each of these phases. Looking at the vertical configuration of the transmission line, we see this yellow line here. We have a little bit higher peak voltage kind of along the center line of our transmission, along our transmission line. And that quickly drops off as you go farther horizontally away from that vertical compared to the delta. And then we have a double circuit vertical transmission tower in this blue. And that's a transmission line that's been optimally phased for AC interference, such that we have from top to bottom ABC phasing and CBA phasing to maximize the magnetic field cancellation as you go along that right-of-way. Now that's all with balanced three-phase operation. In a situation where you have a fault, you end up having a significant phase current imbalance, which results in significant magnetic field strength from one of those phase conductors. And that's going to result in a much more significant inductive coupling as well as conductive coupling occurring during a faulted state. And that can dramatically affect the induced voltages and conductive voltages on your recipient object. Now that we've talked about the physics associated with AC interference, let's talk about some of the objects that are victims of AC interference, or another way to frame that is the recipients of AC interference. Most of you are in the power industry and you're aware of the safety procedures associated with working on de-energized transmission and distribution lines. And part of those work processes were in recognition that you can have coupling from an energized line on the de-energized system that is being worked on. And those processes are often site by site or scenario based and help reduce the personnel's risk when working on de-energized systems, as they can be very dangerous from an AC interference perspective. We're going to focus a little more on objects outside of the power industry, such as pipelines and railroads. And these types of facilities often see more AC interference as they share more corridors with transmission lines. In siting a new transmission line, it's much easier to choose the path that is, or the right-of-way that's already available of a pipeline or a rail. However, it also increases the likelihood of issues from AC interference. There are other objects like cables or buildings that could be recipients of AC interference that could also be examined in these types of studies. First, let's give a little more background about pipelines. So I think one of the important words to note for a pipeline in the pipeline industry is the pipeline appurtenance. These are objects associated with the pipeline, like a pump station, a test site, or a valve. These are often locations that are going to have interface with the personnel and typically going to be a higher level of concern when performing an AC interference study. Another thing to note is what material that pipeline is made out of. It is, if you're looking at it, it's going to be a metallic pipeline, probably steel, and it usually has some sort of coating around that steel to reduce the corrosion of that buried pipe. But that coating, it's acting as an insulator from the earth. It also allows for higher voltages to be induced upon that pipeline from a parallel transmission line. So you can end up with higher voltages when you have a very good pipeline coating. Other things that are important to note about pipelines is that they may have cathodic protection on them, and that cathodic protection could be a passive system, or it could be an energized or an impressed current system. On the illustration on the right, we have a rectifier that is energizing the pipeline, and this allows for a cathodic protection that is tunable and can be monitored. But it's also another spot from an AC interference perspective that personnel are interfacing with that pipeline and could be a new potential hazard. Now, the types of hazards that we're concerned with from a transmission line to a pipeline from a steady state operation process is often a personnel hazard. You can have individuals making contact with an appurtenance and maybe unable to let go. Often an AC interference study looks at a limit of 15 to 50 volts depending on the pipeline owner and their operational practices. Another hazard is the pipeline's longevity itself. And there's a phenomenon known as AC corrosion that if you have a slight defect in the pipe's coating, when you're having that induced current on that pipe, it can drastically accelerate the pipeline's corrosion. And that pipe that was supposed to last 50 years may not make it 5 because of this corrosion. The limits of that often vary depending upon the pipeline owner, but I know that they have observed corrosion, AC corrosion, as little as 30 amps per meter squared. Now, during a faulted state, we have other concerns to worry about. A faulted state, if you remember, we have possibly conductive coupling occurring as well as possibly greater inductive coupling occurring. And this is over a short duration of time, but over that short duration, a person could be exposed to hundreds of volts. And often when we're looking at a personnel limit or what is an acceptable voltage limit for applying any sort of mitigation to a pipeline, we can use some of the calculation methods that are provided in IEEE Standard 80. And if you're not familiar with this standard, it's the standard for a substation's grounding system. And in there, it provides calculation methods to determine a survivable voltage level for personnel working on the pipeline, or in this case, in the substation. Other sorts of hazards that we could see are a coating stress. This is if you have enough voltage between the pipe wall and the soil, you could have a sufficient voltage to exceed the dielectric strength of that pipeline's coating. And that could create more of that AC corrosion farther down the line, or you could even see the possibility of arcing from the transmission line to the pipeline, causing immediate damage of the pipe. Now I want to talk a little bit about railroads and some of the background information about them before we go on to the evaluation of process associated with AC interference. So as you can see on the image of the right, rails are much easier to locate, and the rails themselves are the objects that AC interference is coupling with. So you're going to see the voltages inducing on the tracks themselves. And those tracks are supported by the ties and the ballast material that is holding those tracks in place as the train moves over them. And one thing about ballast of a railroad is that they often have an ohm k-foot value, and they provide this resistance or this ohm k-foot value because of their track signaling systems. So trains can use the tracks themselves in order to communicate or control different aspects of the train occupancy or the grade crossing predictors that can indicate the speed of a train and determine when the arms across a road should come down to prevent traffic from going while the train is in motion. They have multiple different types of control aspects along the train, but we're primarily concerned about AC interference as it relates to their track signaling or those control systems along the track. And much of that track signaling system is placed into control houses, and not every single piece of equipment may be located in the control house, but many of them are co-located in central locations like the control house. These houses help protect it from the environment. They often do have a ground ring around them that can help with the concerns we're talking about with AC interference, but it's possible that ground ring is insufficient for the type of induction or capacitive or conductive coupling that you could see from AC interference or the effects of a transmission line next to a railroad. And another thing I want to mention too is along track signaling, they may have insulated joints along a railroad. And these are points of the railroad that have high impedance path so that the track signaling won't propagate from one track block to the next. And that helps with the train control system, but looking at it from an AC interference perspective, you could have peaks of voltage at those insulated joints. For example, if you had a parallel length of railroad that was inducing, that received or was induced, had 25 volts of induced voltage upon it, that 25 volts may be positive at one point of the insulated joint, and on the other half of the insulated joint, it is negative 25. So you have a total difference of voltage across that insulated joint of 50 volts. and that could be located out on the rail itself or within the control house where all the control cables are brought in. And I mentioned that 50-volt value difference because in a steady state operation of a transmission line, the typical value that we're looking at from a touch voltage perspective or personnel safety is 50 volts, and that's in line with OSHA. Again, we have equipment or signaling concerns in steady state operation. With the signaling controls, it could be as little as 5 volts difference between one rail and another at that 60 hertz that can cause enough voltage imbalance for the signaling to not operate properly. And that could be an issue that allows the arms, such as this grade crossing arm, to come down at times when there is no train, which creates another public safety hazard as people start to drive around those arms as they no longer have confidence in the train signaling, and could cause a train and vehicle collision. And it could also simply damage the train's operation in general. They may have to reduce speed. That costs them, that has a financial cost associated with that in order for their signaling to work correctly at the speeds they want. This is something that is a little device dependent though. So some equipment may be able to withstand 5 volts, 20 volts, 30 volts. Other may be detuned or impaired with as little as 1 volt rail to rail. Again, we have fault state concerns for railroads. Here we have, again, personnel hazards that could be derived. We can derive a applicable touch voltage limit from IEEE standard 80 like we did for the pipelines, or we could reference AREMA that recommends a 430 volt or 650 volt limit depending on the transmission line's protective systems. We also have a possibility of exceeding the signal equipment's voltage limitations, and that could cause permanent damage to the rail's signaling capabilities. And that often occurs around 2 to 3 kV. Again, that's something that you want to review on the specific device capability. So let's talk about the analysis process for AC interference. With most engineering studies, we're going to start with the data. And for a power system, we're looking to understand how the phases are oriented, or the geometry of your phase conductors. We'll want to understand how those propagate along with the planar profile. You'll also need to know the shield wire information and OPGW wire, if it's applicable, what it is made of, and its physical dimensions. And again, the geometry in relationship to the phase conductors. You may need to know the structure grounding, the designed grounding target impedance, or you could be looking at the installed system of any sort of existing facility or existing transmission lines. You definitely need to understand the load current of that transmission line if you're looking at something that has an inductive coupling concern, and the fault current for objects that are simply crossing the transmission line, because you can have conductive coupling from a transmission line just crossing the pipeline or the railroad. For pipeline information, you also need to understand its path, how it is placed within the world, any cathodic protection that is associated with the pipeline, as that determines locations that are accessible to the personnel and different equipment that can be damaged in different situations or different states of that transmission line. You need to understand all of the appurtenances associated with the pipeline, its buried depth, what the material is of that pipeline and any sort of coating that's along the pipeline for determining what the dielectric strength of that coating is, as well as understanding how well that coating insulates the pipe from the soil. In a railroad analysis, you'll need the railroad's alignment drawings and its signaling schematics to understand how track blocks are working and where that railroad is located in the world relative to the transmission line. Any equipment specifications are very useful in determining the 60 hertz limitations, or how robust it is against AC interference concerns. Any ballast resistivity measurements, railroads may have a limit that they operate with. It could be as little as 4 ohm K-foot. It could be as high as 50 ohm K-foot for newly installed material. And different operational practices of the railroad. For example, they may have the ability to operate with an insulated joint that is defective or is in need of repair. And that creates significant imbalance in the rail-to-rail voltage and can dramatically affect the downstream signaling when you incorporate AC interference into that. Or you could have train operators that will occasionally stop the train at different junctions, crossing over those insulated joints, elongating potentially the exposure length of that railroad to the transmission line. And what we end up with is that you have a very complex system with a lot of different pieces from different sources, and it's easiest to evaluate these systems in a software such as XGS Lab, where you can import from your transmission line design model the DXF into XGS Lab, and possibly import the pipeline location and geometry from the pipeline design into XGS Lab and co-locate those into your modeled environment. You can incorporate the transmission line structures themselves, the shield wires, account for how much induction occurs on the shield wires and how that affects your overall magnetic fields at your pipeline. And this is able to account for very complex systems that have multiple transmission lines, multiple recipients, and multiple operation scenarios to evaluate. When you have a modeling software, it makes the process much quicker because it allows you to develop your scenarios, such as your steady state analysis cases, your faulted states, and any sort of recipient operational practices, and run those through the software to determine what your induced coupled voltages are and determine if those are meeting your compliance limits or exceeding your compliance limits. And if you need some sort of mitigation for this, or you're exceeding your limits, you have to rerun all of your analysis typically, because any sort of mitigation effort that you incorporate may have effects on the steady state effect, the steady state results, on the faulted results, and how the recipient, its different operational configurations will be affected. So it's a very iterative process, and typically any change that you make in your model is going to have a cascading effect for the rest of the system. And all of this, of course, needs to be implemented in the real world to mitigate any sort of hazards and reported such that you'll be able to pick up the model or your report so that you can evaluate this system in the future if a new circuit is added to the transmission line or there's a new change to the recipient. Now, I haven't touched on what we actually do if there is a concern of AC interference, but some mitigation approaches can be incorporated into the design phase of either the recipient or the transmission line. The simplest is simply increasing the physical space from the transmission line to the pipeline. As you can see here, we have pipelines that jog to the left and increase the distance from the transmission line to the pipeline, reducing the magnetic field at the pipeline dramatically. If there's a double circuit transmission line, you can also create a phasing configuration that reduces the magnetic field during normal operation. Like we saw with the charts earlier in the presentation of that double circuit transmission line, orienting those so that both circuits are ABC versus a phasing of ABC and CBA makes a significant difference in the magnetic fields along your right-of-way. Something that you can incorporate into the design or into a brownfield or an existing system is counterpoise. This can be a conductor that is either strung along the transmission line, much like a shield wire would work, or it can be buried between the recipient and the transmission line, and that would essentially have a current induced upon it that creates a magnetic field that reduces the end recipient, your pipeline, your railroad's overall voltage. Other approaches that could be applied to the recipient itself could be grounding systems. You could ground the pipeline or railroad in some instances. You may incorporate a gradient control mat to create an equipotential plane in the event of a fault that you're not going to have a voltage difference between a person's feet and the person's hand. You can incorporate different isolation or insulation in order to break up the exposure length of your pipeline or your railroad. You can incorporate non-conductive barriers or add personal protective equipment. Now, a lot of these are different mitigation options. Many of them are not applicable for all situations. You're limited by the operational practices or what's allowed by the recipient or what's allowed by the transmission line. And you may not have complete adherence implementing something like PPE, especially if it's one pump station that they need to wear electrical gloves and every other pump station they do not. It's important to think of those real-world practices and incorporate that into any sort of mitigation design.
Now, before we conclude this presentation, I just want to review some of the information we talked about today by stepping through a case study. So I have a model in XGS Lab of a 230 kV transmission line with an H-frame orientation of the phase conductors, and each of those phase conductors has 750 amps of balanced load. And I have a pipeline that's approximately 50 to 60 feet away from the closest phase conductor that's buried 4 foot into the earth and has a polyethylene coating to insulate it from the soil. The soil resistivity is 50 ohm meters, so relatively low, and that, what you'll see, can cause issues for that AC corrosion that we talked about as a pipeline concern. And the exposure length of this transmission line on the pipeline is approximately 1 mile, where we're directly parallel, and we will have some effects as the transmission line crosses over the pipeline and then departs away from the pipeline. And we'll see that in our voltage plot on the pipeline, as well as our amps per meter squared plot of the pipeline. Also, one thing I want you to see is that XGS Lab is incorporating the sag of the transmission line, as you can see on the XZ plane here and the YZ plane. So it's a very accurate analysis. And another thing to help with that accuracy is we have a portion of the pipeline, or the end of each pipeline, has a Thevenin equivalent of that pipe extending on for infinity. And what this does is it allows the modeled space to be relatively small while not allowing any sort of end effects in your analysis. For example, if you were to simply end the pipeline at these segments, you would see an artificial increase in that pipeline voltage because it just ends in your model, but in reality it continues on to an extent that is insignificant to the analysis itself. So here's kind of our base case. We have approximately 26 or 28 volts as the maximum induced voltage upon the pipeline. And this is a concern, especially if there are any appurtenance in the areas where we have these elevated voltages. And this is a steady state issue, which is going to be present anytime that the transmission line is operating. So when the pipeline personnel are performing their routine tasks like opening valves or checking test leads, they could be subjected to a hazardous voltage at any point. Similarly, we have sufficient induction on this pipeline that we would expect this pipeline to corrode at an accelerated rate because of that AC corrosion phenomenon we talked about earlier. And this sort of sets up our base case for the steady state analysis that I'm going to look at. And we're going to try a couple different mitigation approaches and just compare and contrast how those work. So one method we talked about for mitigation is grounding. In this method, I have incorporated about 300 ground rods in order to reduce the voltage that's induced upon the pipeline. And if you recall, our base case had about 28 volts induced upon the pipeline. We're able to reduce that to about 12 volts that's induced on the pipeline. And these rods are placed or dispersed on multiple sections of the pipe. And one thing to note too, when you're making these sorts of connections, you may not be able to directly connect any sort of grounding to the pipeline. You may need to consider existing cathodic protection, or that whatever you're introducing can cause new corrosion issues for the pipeline. So maybe you need to use steel rods instead of using a copper plated rod for your grounding. So let's see what this does for the AC corrosion. Here we can see that on the pipeline we are just barely below that 30 amps per meter squared value. Here's another view of the pipeline's amps per meter squared value. And by incorporating those ground rods throughout the pipeline, we're able to keep it just below the level where we'd expect to see corrosion occurring on that pipeline. So we can also try breaking the exposure length of that pipeline to reduce how much voltage is induced upon the pipe. And we can do that using insulated joints. And again, this is just highlighting the difference of different options for mitigation of a pipeline. So here we have each of these rectangular symbols, and these are high impedance points along the pipeline that break the electrical continuity of the pipeline. And again, we're looking at a steady state analysis for this case study. When you're really incorporating this type of mitigation, you may have additional concerns during the faulted state, because during that faulted state you can have significant induction again for a short period of time, but that is a significant induction and significant voltage that can break the dielectric strength of this insulated joint intended to protect you from AC interference, and it's really causing a new issue to resolve. So when you incorporate those breaks or those insulated joints in the pipeline, you're reducing the length of exposure for the pipe. And by doing that, we're able to reduce the voltage to less than 12 volts that's induced upon this pipe section. And that reduces our AC corrosion, or our amps per meter squared, again to acceptable limits below that 30 amp per meter squared value. Here we can see the rather dramatic effect that those insulating joints make on that amps per meter squared value, as you can see these drastic peaks occurring at each one of the insulated joints. Now, one thing to consider again is that each analysis is unique and there are many options available when trying to mitigate AC interference, but it is very dependent upon the system owners as far as what is actually going to be a practical solution and what may actually cause more harm. And insulated joints is one of those examples where many pipelines may not be able to insert an insulated joint, um, as they may not be able to either disable the pipeline or the physical strength required to pass whatever the pipeline is containing. It could be a high enough pressure that there's not an insulated joint strong enough to contain that material. So grounding may be your only option in some instances, or aerial counterpoise, or some sort of other shielding. Regardless of what you're looking at, though, I think it's important that AC interference studies are obviously rather complex, and you're typically going to be evaluating multiple scenarios when you're looking at those types of challenges. And you're looking at these primarily to reduce hazards for personnel and reduce equipment damage. When you're looking at AC interference, you really should be looking at multiple scenarios and let the tools help you in determining cost-effective solutions to mitigate any sort of challenges that you're dealing with, whether it's an inductive challenge or simply a conductive issue. You can find solutions using software and iterating through different types of analyses or scenarios. So at this time, I'm going to open up to questions and give a little bit of time before we conclude this webinar.